Hello, this will be our first video in a series in Chapter 3 for Garrett's Biochemistry. So in this video, we're going to consider some thermodynamic concepts, and we're going to be looking at delta G and delta G naught, and also KEQ. So I want to give you the need to know in this chapter because there are a lot of concepts that are introduced in this chapter that are not really tested on. And so I want to just give you the information that you really need. In this set of videos. Okay, so let's first consider a reaction that is reversible, where we have A plus B going to C plus D. So remember this from general chemistry. We talked about this then, that for a reaction A plus B is going to C plus D, we can write a KEQ. We can write an equilibrium constant for that reaction where it is given by the concentrations of C and D, or products, over A and B, which are the reactants, at equilibrium. So the KEQ, or the equilibrium constant, is given by the concentrations of products over the concentrations of reactants at equilibrium. So we could even write products over reactants. So those concentrations at equilibrium, okay? And so delta G is a free energy change, and we can give that free energy change for non-standard conditions by this equation. Delta G is equal to delta G naught plus RT, where R is the gas law constant, T is equal to temperature, ln of concentrations of C and D over A and B. And this is where we're not at equilibrium. This is the free energy at any snapshot in time for this reaction. But if we are at equilibrium, we can say that delta G is equal to 0. So at equilibrium, the free energy change is equal to 0. And we know that the CD over AB is equal to our KEQ. So we can plug in for this equation. We can say that if this delta G is equal to 0, then we can move delta G naught to the left and say delta G naught is equal to negative RT ln of KEQ, because if we move this to the left side, it becomes negative, and that'd be negative delta G equals RT ln of KEQ. But if we want to make delta G positive, then we need to take the negative of that. We can also convert that to this equation. Delta G naught is equal to negative 2.3 RT log to the base 10 of KEQ, which can be rearranged to give us KEQ is equal to 10 to the negative delta G naught over 2.3 RT. Okay, we're going to use all of these equations in our calculations. But let's consider what this delta G looks like on a graph. And I thought about this a little bit before I decided to define it this way, because I haven't seen anybody else do it this way, but I think it will help clarify some things for us, okay? So let's plot delta G, or change in free energy, on the y-axis, okay? And let's say that our products are over here on our x-axis, and our reactants are over here on the left, okay? So as we move to this way, we're going to be increasing reactants, and as we move to the right, we're going to be increasing products, okay? And let's also say that our zero line is not on the x-axis. Let's say our zero line is here, just for clarity. Okay, so we could have different types of reactions. We could have different reactions where we have different conditions. We could have a condition where we have an equal number of products and reactants at equilibrium. So remember, delta G is equal to 0 at equilibrium. So at equilibrium, our delta G is going to be on this 0 line. And as we move away from equilibrium, as we increase our reactants, our delta G is going to increase. Okay? And as we increase our products, our delta G is going to increase. So we get this parabolic curve for these reactions. Okay, now it may be a shallower parabola or a wider parabola, it doesn't matter. I'm just saying theoretically. Okay, so we also could have a situation where at equilibrium we have more reactants than products, okay? And that would be given by this. So as we move away toward, as we increase our reactants, we're going to increase the delta G, and as we increase our products, we're going to increase the delta G. And so we could have a situation where we have, I don't know what color to use, where we have more products than reactants at equilibrium, and as we increase the reactants, we're going to increase delta G. As we increase the concentration of products, we're moving away from equilibrium, we're going to also increase the delta G, okay? So remember, delta G is equal to 0 at equilibrium. So at equilibrium, our delta G is 0. And as we increase, as we move away from those concentrations of reactants and products, we're going to be increasing our delta G. Or as we increase the delta G, we're going to be moving away from those concentrations of reactants and products. Okay, so let's go down and look at some conclusions here. So we can say that delta G naught, remember delta G naught is given by negative RT ln of KEQ. So the only thing that really changes here is possibly temperature and the ln of KEQ. So these values are dependent on temperature and pressure, okay, but they're also dependent, delta G is also dependent on the concentrations of these reactants and products for each system, and those concentrations are going to be equal to KEQ at equilibrium. So delta G is a measure of equilibrium conditions for our system. So delta G is a measure of how far, delta G naught is a measure of how far from equilibrium our reaction is under standard state conditions. So what does that mean? It means that, remember that standard state is 1 molar for concentration for all of our solutes. It's going to be 25 degrees C for our temperature and 1 atmosphere of pressure. So this is delta G naught, okay? Now, if we have delta G naught prime, then we use that oftentimes for biological systems, and that's the same as delta G, but it means that remember that our system is also dependent on pH. And so we want our system to be at a neutral pH in biological samples. So delta G naught prime is going to be at a pH equal to 7, and so that means our hydrogen ion concentration is going to be equal to 1 times 10 to the minus 7 at delta G naught prime conditions. But we're not at prime conditions right now. We're talking about just delta G naught conditions. And so if our delta G naught is negative, remember if our delta G naught is, let me go down a little bit. If our delta G naught is negative, that means the reaction is favorable. And if our delta G naught is positive, that means the reaction is unfavorable. So if our delta G naught is negative, okay, then we're going to be moving toward reactants. We're going to be moving toward products to reach equilibrium. If our delta G naught is positive, then we're going to be moving toward reactants to reach equilibrium. So delta G naught is a measure of how far. So if our delta G naught is a measure of how far away from equilibrium we are under these standard conditions. How far away from equilibrium we are under standard conditions, okay? So if our delta G naught is close to equilibrium, okay, then we're not far away. If our delta G naught is close to 0, then that means we are close to equilibrium under these standard conditions. So let's look at these equations again. Delta G is equal to delta G naught plus RT ln of CD over AB. That's not at equilibrium. If we're at equilibrium, then delta G is equal to 0, and delta G naught is equal to negative RT ln of KEQ. And then we have these other equations that we can use to get, if we have base 10 logarithms, or if we want KEQ itself. Okay, so we'll begin to do some calculations in the next video.